Let's start the lecture for today. I have my voice back, not quite 100%, but should be okay. So lecture 16, we'll now start to talk about circuit elements that we use in AC circuits. Because we started we started this module of the course talking about what a magnetic field is, and that current will create a magnetic field. But then if you have changing magnetic field, that also creates a current. And that's what we learned when we talked about Faraday's law, right? Faraday's law says that if you have a changing magnetic field, that creates a changing magnetic flux. Magnetic flux is just the number of magnetic field lines that's crossing a loop. And if that's changing, then you induce a voltage, which we also call EMF, through that loop. And of course, if you have resistance through that loop, Ohm's law, V equals IR, tells us that the induced voltage induces a current, right? So mathematically, we represented Faraday's law in this equation. If you have a changing magnetic flux, right, then that creates a voltage through a loop. And if your loop has n turns, then the voltage is created in each of the turns. So we multiply the change in flux by the number of loops or number of turns. We learned the magnetic flux. We defined what it is, and we saw that it depends on the magnetic field strength, the area A of the loop, as well as the angle between the magnetic field and the normal to the area. In essence, you can change any of these variables, magnetic field, area, and angle, in order to change the magnetic flux and therefore create a voltage through the loop, right? So that's what we learned when we talked about Faraday's law and how we can generate a current if you have a changing magnetic field. And then in the last lecture, we learned about the transformer, which is essentially a direct application of electromagnetic induction or Faraday's law. We learned that if you have a primary coil, right, on one side of this iron core, and you apply, right, an alternating voltage through that coil, therefore you'll have an alternating current through the coil. If you look at the behavior of an alternating current, the magnitude of the current, or the size, amplitude of the current, changes with time, and therefore that creates a magnetic field that's changing in magnitude as well, right? And we saw that in the last lecture, that the magnetic field will then go through the second coil, which we call the secondary coil. And since the magnetic field magnitude changes through the second coil, that then induces a voltage in the secondary coil. So the secondary coil voltage is the induced voltage that is a consequence of the changing currents and the changing magnetic field produced by this primary coil, right? So that's a direct application of Faraday's law, where we have two coils and they're not even touching, but because the current in the first coil is changing, you induce a voltage in the second coil, and essentially you then induce a current in the second coil. So that idea, that example of the transformer, is the concept behind mutual inductance, right? You essentially have two coils. In one coil, you may have a changing current, which produces a changing magnetic field. And as a consequence, you have a changing magnetic flux through the second coil, which then produces a current in the second coil, right? And if we follow through Faraday's law, we will see that the voltage that you create in the second coil will be due to the change in the current in the first coil. And likewise, if you have a changing current in the second coil, right, di over dt here, changing current in the second coil, that will also create or induce a voltage in the first coil, which is this EMF or voltage in coil 1. right? So that's the whole concept behind two coils close to each other. And if you have a changing current in one, that creates a voltage in the other, and vice versa. If you have a changing current in coil 2, that creates a voltage in coil 1. The negative sign here in this equation follows from Lenz's law. When we were talking about Faraday's law and talking about the direction of the induced current, because of the induced magnetic field, Lenz's law says that the induced EMF or the induced current that's created will oppose the change in the flux. And so that's carried over in these definitions here, meaning the voltage that's created in coil 2 because of the change in current in coil 1 is a consequence of Faraday's law, and the direction of current produced in coil 2 will depend on whether the current in coil 1 is increasing or decreasing. Okay. Right. So now let's define this variable, right? So we see this variable M coming into this equation here. This variable M is what we call mutual inductance, which then, because Faraday's law tells us it's the change in flux that changes the voltage. So the flux is carried by this variable M, which we call mutual inductance. Okay, so the mutual inductance tells us that, say, the flux, in this first form for the mutual inductance, if you have a current in coil 1, right? So that's the current in coil 1. It will create a magnetic field, and the magnetic field created by the current in coil 1 will manifest as flux through coil 2. Right, so that you have the current in coil 1 producing a flux through coil 2, and of course the flux or the magnetic field lines through coil 2 will pass through each turn in coil 2. Right? And likewise, if you have a current in coil 2, right? So if you're talking about the current in coil 2, then the current in coil 2 will create a magnetic field, which will then have magnetic flux through coil 1. So this equation here tells us that the current in coil 2 will create a magnetic flux that will pass through each of the turns in coil 1. Okay. And it's the same. So the definition, this M refers to the same thing. It's just a matter of whether you're looking at the current in coil 1 or the current in coil 2. And mutual inductance has a unit of Henry, capital H. It just tells us, it's a property of the coils that tells us how much these two coils will affect each other. So it's a shared property of two separating independent coils. If you have a high mutual inductance, that means that the current in coil 1 will generate a large voltage in coil 2, and coil 2 is highly affected by coil 1. Right, so let's see how we apply this equation, because mutual inductance has two forms. Either it's the current in coil 1 that produces flux in coil 2, or the current in coil 2 that produces flux in coil 1. So say in this scenario where you have a long solenoid, right, with length L and cross-sectional area A. Right, so we're talking about this long solenoid here, and it contains N1 turns. And then a second wire is wrapped around the solenoid. The second wire has N2 turns. Right, so the subscripts here help us identify, right, coil 2 has N2 turns, and the solenoid has N1 turns. Those N1 turns carries a current I1. Okay. We want to calculate the mutual inductance. So of course, mutual inductance will be the same regardless of which equation you will use. It's just a matter of which variables you know. So here you're given the current I1. Okay? Because it's I1 that you know, and you're not given current I2, it just makes sense that this first equation is the more useful form for for calculating the mutual inductance, right? Because I1 is given. Okay. It's now a matter of finding what is magnetic flux through the coil 2, right? I1, that's given, N2, that's also given. So it's a matter of finding what is the magnetic flux through coil 2 in order to find the mutual inductance. And we know that magnetic flux is defined as B times A times cosine theta. Now it's we're looking at the magnetic flux through coil 2. We want to find how many field lines are crossing coil 2. But remember that it's the current in coil 1 that generates the magnetic field that crosses through coil 2. And hence, the magnetic flux through coil 2 will depend on the magnetic field generated by coil 1. And that's why you have a subscript of 1 there for the magnetic field. Because the current is in coil 1, the magnetic field is produced by coil 1. And of course, the area is the area of the solenoid coil 1. Okay, and because it's the solenoid that carries the current, it's the solenoid that produces the magnetic field, the magnetic field B1 is then will then come from the definition of the magnetic field created by a solenoid, right? So this is from definition, the equation of the magnetic field created by a solenoid that carries a current I. N, of course, is the number of turns, L is the length. So we then substitute this definition of magnetic field of a solenoid to the flux through coil 2. Hence, you have the flux through coil 2 is the whole equation for the magnetic field of a solenoid times A. Of course, that A is coming from this A here, the definition of magnetic flux. Right? So then it's a matter of substituting this flux definition into the mutual solenoid equation. You have mu naught is coming from here, magnetic field of a solenoid. N1 also comes from the magnetic field of a solenoid definition. N2 is coming from here, the definition of the mutual inductance. The area comes from the definition of flux, and the length is from the definition of the solenoid. Right. So you have here that the mutual inductance, or these two coils, will affect each other depending on the number of turns of each coil, the length of the solenoid, the area of the solenoid, and it also depends on mu naught. So mu naught is called permeability of free space. Okay? It's material dependent. If you have nothing inside the solenoid, then mu naught is equal to mu naught in air, 4 pi times 10 to the negative 7 Tesla meter per ampere, right? But if you put like an iron rod in the core of the solenoid, then mu naught becomes mu, which is the permeability of the material, which you can look up in some tables. Right? Okay, so that is mutual inductance. It tells us how one coil affects another coil in terms of generating a voltage in the second coil. Now, if you have a single coil, as shown here, and say, for example, you have current flowing through your coil, of course, we already learned that whenever you have current, that current will generate a magnetic field. Right-hand rule, from right-hand rule, you point your fingers in the direction of the current flow, and the thumb points in the direction of the magnetic field. So the magnetic field generated will be pointing from right to left inside the coil, as shown in this figure here, right? So you have this magnetic field here. But then when you change the current magnitude, for example, at the moment when you close the switch, so you have this sudden jump sudden increase in the current, or when you open the switch, when you have a sudden decrease in the current, you then have a change in the current through this coil. And according to Faraday's law, again, if you are changing the current, then there should be an induced voltage or an induced current, right? And since you only have one coil here, the current that is induced and the voltage that's induced will be induced in the coil itself. Okay? And that's why it's called self-inductance. So you have sort of like this opposing current to the already existing current. Okay, so self-inductance, because you have a single coil, it's like there's no nearby coil that will be affected by the changing current. And so it's the coil itself that gets affected. Okay, and like before, the voltage that is created in the single coil will depend on how quickly the current changes. Okay. So any change in the current will produce a voltage or an EMF in the coil itself. Again, the negative sign here is a consequence of Lenz's law, which says that you will induce a voltage that will oppose the change in the current in the coil. Okay. L is a property of the coil, which is called the self-inductance, right? It again is related to the number of magnetic field lines that crosses that coil and the current that produces the magnetic field through that coil. So it's a similar concept to mutual inductance in that it tells you how much the coil is affected, except that in self-inductance, because you only have a single coil, there's no other nearby coil that gets affected but the coil itself. Right, so we're just talking about a single coil, the current through that coil, and the magnetic flux through that coil, of course, and is the number of loops. Right, so just a quick example to see how this equation applies for the self-inductance. Say you have a solenoid, and that solenoid has a cross-sectional area a length L, and N turns, okay, and coils. We already know the magnetic field of a solenoid, and the magnetic flux is defined as BA cosine theta, and we want to find the self-inductance of that solenoid. How much will the self-inductance will, of course, then relate to how much voltage will be induced in that coil if the current changes. Right. So from definition, the self-inductance depends on the number of turns, which is given. It depends on how many field lines is crossing that coil, which is defined as BA cosine theta in this case, right? We're talking about the angle, if you have a solenoid like this, and the magnetic field here, of course, the normal vector is parallel to the magnetic field, and hence cosine theta is equal to 1 because theta is equal to 0. And hence flux is just equal to BA. So we combine that, then flux is equal to the magnetic field of a solenoid, mu naught N over L times I, times the area, cross-sectional area of the solenoid. You have there the flux through that solenoid there, which then when you substitute into the self-inductance equation, right? Because we're talking about the same coil, then you have the same number of turns, hence you have N squared, number of turns squared in your resulting equation for self-inductance. Okay. But what this equation tells us is that the self-inductance, or how much voltage is produced in the coil as a result of the changing current in the coil, depends on the geometry of the coil, meaning the size and the shape comes into the cross-sectional area and the length of the coil, right? It depends on cross-sectional area and the length of the coil. It also depends on the number of turns in. And you again have this permeability dependence. Of course, if there's nothing in the center of the solenoid, then it's just permeability of free space. But if you put something in the core or inside the solenoid, then you have to account for the permeability of the material, for example, iron or some other material. Right, so self-inductance and mutual inductance, it's a property of the coil, but it's not just a property that you look up in a table. It depends on other variables, like the shape, the length, number of turns, and the only thing you look up in the table is the permeability constant, right? But the inductance, I mean the self-inductance, which tells you how much the coil affects itself, is the property that is needed to create this circuit device called the inductor. Okay, so the inductor, it's designed to have a particular self-inductance. And the purpose of that self-inductance, right? Self-inductance kicks in whenever you have a change in current. According to Faraday's law, the induced current will oppose the change in current. So the purpose of the inductor will oppose the variation of the current through the circuit. So it sort of acts like a resistance that impedes the alternating current, right? When we were talking about direct current circuits or DC circuits, we learned about the resistor. The resistor impedes the flow of charges and therefore controls how much direct current is flowing in your circuit. For an AC circuit, or you have an alternating current, right? An AC circuit, alternating current, we learned last time, means that the magnitude of your current changes with time, right? And because the amplitude of your current or size of the current changes with time, Faraday's law says that it will induce a voltage. And the resistor that induces that change in voltage is the inductor. So it's like the inductor is the counterpart of the resistor, except for inductor, we refer to it in AC circuits. Okay? And it's a quite an important circuit device because it makes it difficult for rapid changes in current to occur, because of the self-induced EMF that opposes any change in the current. So any sensitive equipment that is easily damaged by surges in current or surges in voltages will need to have an inductor in order to protect these circuit elements, okay, from any rapid changes in current. Does that sort of make sense? What an inductor is? Yep. So just to drive the concept of the inductor and self-inductance, say a control, of course, a switch controls a circuit. You turn on the switch, current flows because you complete the circuit. If you turn off the switch, the current disappears, or the current stops flowing because you have an open circuit. So for example, you close, is a spark more likely to be produced if the switch is closed, or is it likely to be produced if the switch is opened, or does it matter? Meaning, will the spark always be produced if the switch is closed or opened? What do you think? The spark we see is, of course, electrons jumping from one part of the circuit to another, right? Yeah, good. Yeah, the answer is when it's open. And see why. Lenz's law says that, whenever you have a change in current in your circuit, there will be an induced current that will oppose the change. So if you think about a circuit that is first closed, open, say you have this circuit here, it's opened like this. So initially current is not flowing in your circuit, right? There's no current flow. When you close the switch, right, current will of course be able to flow because you're completing the path, but Lenz's law says that the current will not flow immediately. because you're going from a zero current to some current value. In essence, you're going from zero magnetic field to some magnetic field value, and Faraday's law will oppose that change. So it will create a magnetic field that will oppose the current flow. So momentarily, there's still zero current for a very short time before current is able to flow. But then if your circuit is already closed to begin with and current is already flowing, when you open the switch, then Lenz's law says, I would like to maintain some current flow in the circuit. And so induced current will be produced to sort of bridge the gap, so that the current does not immediately go to zero, but it will go to zero slowly. And that's why you then produce a spark, because the circuit that's opened very quickly needs to produce an induced current in order to bridge the air gap. So that's right. Yeah, the spark will be produced when you open the switch. And does that make sense? And that's why you are told not to yank the plug of the circuit, of the outlet, because that will create a spark. Yeah. Usually, if you don't want the spark to be created, you turn off the switch and then yank the plug. Okay. In fact, look at what happens. Watch this video. It's a high voltage power line. Of course, very high currents are flowing through this line. What do you think will happen if the line breaks? So that's exactly what happens if the line breaks. The spark you see is induced current that will try to bridge the gap in order to prevent that sudden decrease in the current through your lines. Right? Good. Make sense? Yeah, it's enough to fry. Okay. Right, so for any changing current, like the video I just showed, for any changing currents, there will be an induced voltage to try and oppose the change in current. We can calculate the change in voltage from the induced EMF that we've seen earlier. So it depends on how quickly the current changes and the self-inductance of the inductor. Right? It doesn't depend on the current per se. So there needs to be a change in current for voltage to be produced. And when the inductor produces this voltage to oppose the change in current, work will be done. And the work done to increase the current such that to oppose any change will be stored in the magnetic field of the inductor. And so in essence, inductors also store energy. It stores energy in the magnetic field, and the amount of energy stored is given by this equation here. 1/2 Li squared. It sort of looks familiar if you compare that to the energy stored in a capacitor. The energy stored in a capacitor depends on the capacitance of the capacitor and the voltage across the plates. But of course, in a capacitor, the energy is stored in the electric field. Okay. Whereas for the inductor, the energy stored depends on the inductance of the inductor and the current that's flowing through the inductor, and the energy is stored in the magnetic field. So sort of the inductor is sort of a cross between the resistor, which opposes changes in the current, and the capacitor, which is able to store energy. Okay. Of course, when energy is released, so if the inductor can store energy, the inductor can also release energy, and the amount of energy it can release is equal to the maximum energy it can store. Okay. All right, and in the next lecture, we will look into more detail about analyzing circuits containing inductors and containing an inductor. But to wrap up our lecture today, let's just look at this exercise trying to combine what we learned about inductance and the inductor. So you have two solenoids. Okay, we label the solenoids S1 and S2. S1 is the first solenoid, S2 the second solenoid. They share the same cylindrical axis, meaning you have one solenoid is smaller and the second solenoid wraps around the smaller solenoid. The first solenoid has 400 turns, so S1 refers to 400 turns, and S2 has 700 turns. Okay, a current of 3.5 amperes is flowing in solenoid 1. Okay, that produces a flux of 300 microwebers through each of the turns of solenoid 1 and 90 microwebers through solenoid 2. And we are given here some questions that we need to answer. Right, let's look at the first question. So mutual inductance, right? Mutual inductance is whenever you have two coils that are close to each other, whether they are concentric, meaning they share an axis, or whether they are just side by side, they will affect each other according to their mutual inductance. So that's what we want to calculate. Mutual inductance is defined by these two equations. It depends on the magnetic flux. So you have a current in solenoid 1. The current will create a magnetic field which will pass through solenoid 2. So each turn in solenoid 2 will have this number of magnetic field lines defined by the flux. Likewise, the current in solenoid 2 will create a magnetic field, and the magnetic field will cross each of the turns in solenoid 1 according to this magnetic flux through solenoid 1. Okay. And you can use either of these equations. It will still give you the same answer for the mutual inductance. But the clever choice of which equation to use will depend on what you know, right, from the problem. So what you know from, which equation to use, right? The problem gives you the current in solenoid 1, right? Right. So although this second equation is valid, you can also use that. You know the number of turns in solenoid 1, it's 400 turns. You know the flux through solenoid 1, it's 300 microwebers, but you don't know what the current is in solenoid 2. Hence, that will prevent you from using the second equation. Right. So it makes sense to use the first equation, right? The number of turns in solenoid 2. That solenoid 2 has 700 turns. Okay, the flux through solenoid 2, right, is 990 microweber, right? Don't forget to convert micro to times 10 to the minus 6, divided by the current in solenoid 1, which is 3.5 amperes. Good, so then that gives you the mutual inductance for both solenoids. Okay. If you know the once you know the mutual inductance, you can then use that to calculate how much current I2 is produced in solenoid 2. Okay. Because this M is the same M as that and the same M as that. So there could be a follow-up question that will ask you how much current is produced in solenoid 2. Then use this mutual inductance you've calculated to solve for that current I2. Okay. But for the second question, you want to calculate the self-inductance in solenoid 1. So because the current, because you have magnetic flux through solenoid 1, okay, you can calculate the self-inductance for solenoid 1, and then how much energy is stored in its magnetic field. Right, self-inductance is defined as the number of turns times the flux over the current. And we're just talking about one solenoid. So if you notice, the subscripts all refer to solenoid 1 because that's what we want to consider, the self-inductance of solenoid 1. So we want the number of turns through solenoid 1, which is 400. The magnetic flux through solenoid 1 is 300 microweber, so 300, and again, don't forget to convert micro to times 10 to the minus 6. And then the current through solenoid 1, 3.5 amperes. So you get the self-inductance of solenoid 1, and then the energy that's stored in the magnetic field is 1/2 times the self-inductance times the current, right? You've calculated the self-inductance here, so that goes into the energy equation. Of course, the current is given in the problem. Right? Good. And then how much voltage or EMF is produced in solenoid 2 when the current in S1 increases at a rate of 0.5 amperes per second, right? So the current is now changing 0.5 amperes every second. Because of the change in current, you induce a voltage in solenoid 2, and that's what you want to find. Right? From the very beginning of this slide, we said that if the current in one coil changes, that produces a voltage in the second coil, and that depends on how much these coils affect each other, meaning the mutual inductance M. Okay. We want to find, and we said the negative sign just gives you the direction. It's just Lenz's law. And what we want is it's just the voltage. Hence, we can just get the absolute value disregarding the negative sign. So we know the mutual inductance from before. We've calculated that. That was the first question, was to calculate the mutual inductance between the two coils. We calculated that as 0.018. And then the current is changing at a rate of 0.5 amperes per second. So you have change in current is 0.5 times the mutual inductance will give you a voltage of 9 millivolts that's being produced in the second coil. Okay. Right. As a follow-up, if you're given the resistance R in second coil, S2, you can then calculate the induced current, right? The current in the second coil will then be the voltage in the second coil times the resistance. I'll just write the voltage as V, right? This E means voltage or EMF. So it all follows through, it's all connected to what we have been learning so far. So first, what you can calculate is the voltage because of the changing current. And then if you know the resistance in the coil, then you will be able to calculate the induced current in that coil using Ohm's law, which I think my Ohm's law here is wrong. So this should be currents is V over R from V is equal to IR. Any questions about the exercise or the solution? And so I hope the concept of the inductance makes sense. It's essentially a property of the inductor that opposes any change in current or voltage in a circuit. Because in the next lecture, we will then look at analyzing circuits where we combine the inductor with a resistor and combine the inductor with a capacitor, seeing what will happen in with the current and the voltage in the circuits, right? So if you don't have any lecture, if you don't have any questions, then I will end the lecture here on inductors and inductances, and I will see you in the next lecture tomorrow. So have a good day, everyone. We finished quite early today.